Hello again, Physics 243. In this unit, we'll talk about the behavior of gases. One little side note, I'm kind of bothered by the spelling of gases, but I'm even more bothered by this word with only one S. According to the dictionary, both are correct. So I decided to go with this one, but it still looks weird to me. Anyway, behavior of gases. Well, I'm assuming that most of you have taken some chemistry or something, even in high school, and you have heard of the ideal gas law. Law is in quotes. It's not really a law like Newton's laws are. But here it is. And what it does is it relates these characteristics of gases, the pressure, the volume, and the temperature. So if you change pressure, volume, and temperature of gases, they will change, these things will change one into another according to this relationship. So pressure is P, V is volume. What about N? N is the number of moles of gas that you have. The R here is a number called the universal gas constant, and it works for any gas. Well, any ideal gas, I'll put it that way. And by that I mean any gas which is sufficiently dilute to behave like an ideal gas. I'll talk a little bit more about that in a moment. Anyway, R is a number, universal gas constant, and this is its value with these units. And then T is temperature, which should be reported in degrees Kelvin, as you see here. I'll say something about Kelvin in a moment. Okay, so as I was saying, this ideal gas law works well for whatever gas as long as it's sufficiently dilute and the temperature is not near the liquefaction point. Basically, what you need for an ideal gas is for the gas molecules to not know that any other gas molecule exists. The gas molecules must not interact with each other, and that gives an ideal gas. If molecules collide, then they can collide and be perfectly elastic collisions. But for the most part, the particles don't know that each other exist. And that's why you need to dilute gases in order to really see this behavior. However, for room temperature and atmospheric pressure, real gases really do behave according to an ideal gas law pretty accurately. Air, nitrogen, oxygen, hydrogen, noble gases, etc., carbon dioxide. This is a very good description of such gases at room temperature and atmospheric pressure. Okay. A couple of historical discoveries are incorporated into the statement of the ideal gas law. Boyle's law, 1662. He was not the first to observe this, but he was the first to, I guess, formulate it. At constant temperature, pressure times volume is constant. Wikipedia says that this law was the first physical law to be expressed in the form of an equation describing the dependence of two variable quantities, pressure and volume. That's an interesting little historical tidbit. You have to remember the state of science in 1662 is not what we kind of think of science these days. They were really, blazing the path for us. Another interesting little side note, guess who built the material, the laboratory apparatus, as it were, that Boyle used to make this observation and formulation? Robert Hooke, the same Hooke from Hooke's law, and the same Hooke that gave the name cell to a biological cell. All right, Charles's law. This goes to 1780. So this observation, which is that volume is proportional to temperature, the volume of a gas is proportional to temperature, really had to wait for Fahrenheit to establish thermometry and methods to really accurately measure temperatures. So it was like 100 years here, more than 100 years, before this could really be established definitively, let's say. Not too long thereafter, here's Gay-Lussac's law, which is that the pressure is also proportional to the temperature. So basically, put these all together, and you get this with the N and the R, which has to be put in. Okay, so here's an interesting implication of Boyle's law, which is that the volume is proportional to the temperature. So what this means is that if you plot the volume of the gas versus temperature, and here what you want to do is have a fixed pressure, you get a straight line with a certain slope, right? Well, positive slope. So as things get hotter, the volume increases. But you could extrapolate this back, or do experiments as to the left, as cold as you could possibly get, and then extrapolate it. And if you extrapolate it, it goes back to this value here, negative 273, actually 273.15. And here I'm using the Celsius scale. It has to be an extrapolation. That's why these dotted lines are here, because a real gas, as you get colder and colder and colder, it'll start to liquefy eventually. And so when that happens, it's not behaving like an ideal gas law at all anymore, because the molecules are influencing each other. And that's what happens when a gas liquefies. But nevertheless, you could do this experiment with different gases, fix the pressure and see volume versus temperature, and the various lines that you get will extrapolate back to the same point here, negative 273. So that's an interesting implication. And it took a long time, until Kelvin in the 1800s, to sort of make sense of that. So that's why the Kelvin temperature scale is basically the Celsius temperature scale, but shifted so that the 0 is now over here. So that's the Kelvin temperature scale, which is what you use scientifically. And 0 degrees Celsius equals 273.15 degrees Kelvin. So that's so somewhere over here, right? Okay, why? Well, Kelvin had lots of reasons for doing this, besides what we talk about in this class. But it is convenient because we don't have to deal with negative values of temperature, right? Over here we have negative values of temperature in Celsius, and that kind of screws up the formulas a little bit. Things turn negative when they don't really mean to be negative. But it is kind of curious that if you extrapolate this back, it crosses the axis here. And if you go even colder than that, it would imply you have a negative volume, which doesn't make any sense. So 0 degrees Kelvin is really the minimum temperature that you can have. Things basically stop moving completely at that point. And really, you can't get there. The coldest you could possibly get are micro degrees near 0 degrees Kelvin in highly specialized laboratories. But scientifically, in scientific formulas and things, you're going to want to use the Kelvin temperature scale. Often you will come across standard temperature and pressure, so STP. You probably know this from chemistry class. And the standard temperature is 0 degrees Celsius, which, as we just talked about, is 273.15 degrees Kelvin. And standard pressure is 1 atmosphere. So 1 atmosphere at sea level, which is 101.3 kilopascals. Okay. So most things are defined in terms of STP, and this is what STP is. So good to know. Here's another thing that's good to know, one of the examples in the book. What is the volume of 1 mole of an ideal gas at standard temperature and pressure? So that follows right from the ideal gas law. Solve it for the volume, plug in the numbers. So here I have 1 mole, the ideal gas constant, and notice we have degrees Kelvin, right, as I mentioned before, and the temperature in terms of degrees Kelvin, so that nothing is going to turn negative on us. And the pressure, standard pressure, is down here, denominator. Put that in a calculator and you get this number, 22.4 times 10 to the minus 3 cubic meters, which is 22.4 liters. A liter is a cube that's 10 centimeters on the side, or 10 to the minus 3, right? So 10 to the minus 3 meters cubed, 10 to the minus 3 meters cubed is a liter. So this is something that's good to know. The volume of 1 mole of an ideal gas at STP is 22.4 liters. Right, that's what it says here. The volume of 1 mole of an ideal gas at STP, 22.4 liters. So interesting curiosity, example 1314, how many molecules are in 1 breath? And let's approximate 1 breath to be 1 liter, 1 breath of air. This kind of will give you a sense for kind of the size of molecules, how many molecules there are in things. All right, we start with 1 liter. And to do this, we basically just change units. So unit conversions are surprisingly powerful. let's just convert units here. Well, we have this equality at the top of the screen here, so you can convert liters into moles. And so 1 liter, 1 breath, is about this many moles, 0.045. And now we know that 1 mole is this many molecules, 6.02 times 10 to the 23. So we do another unit conversion from 0.45 moles into molecules using this equality. The answer is approximately 3 times 10 to the 22 molecules. So every time you take a breath, 10 to the 22 molecules are moving in and out. 10 to the 22, that's a 1 with 22 zeros after it, and maybe times 3 or so. That's a huge number of molecules. So these numbers are so big that we really have no clear intuitive understanding of them. It's just a humongous number of molecules. Okay, that's really all I want to say in this brief introduction to behavior of gases. Next up, we'll talk about kinetic theory and some of the important results that come from this. Okay, see you then.